In this video, we examine a single conclusion. Humanity will never leave the Milky Way. Not because of a lack of technology, and not because of a lack of ambition, but because of limits built into physics itself. We will look at three constraints that define every civilization: distance, energy, and time. Using real measurements and established physics, this video explains why interstellar expansion remains out of reach. Not temporarily, but permanently.
Every sci-fi movie you've ever watched presents an incomplete picture of the future. Interstellar, Star Wars, galactic travel. None of it reflects what physics actually allows. Here's the truth no one likes to admit. Humanity will never leave the Milky Way. Not in 10,000 years. Not in a million years. Never. This isn't pessimism. It's physics. Because the universe imposes strict limits on every civilization. Limits defined by three fundamental constraints: the speed of light, energy conservation, time dilation. Any one of them alone is enough to end the idea of interstellar expansion. Right now, the fastest object humanity has ever built has been traveling for 47 years and has covered only 24 billion kilometers. That sounds impressive until you realize that at this pace, leaving the Milky Way would require about 1.6 billion years. By then, Earth itself would no longer exist. This is one of the universe's harshest realities. It allows you to observe endless stars, but does not permit access to them. So the real question isn't how we escape. The real question is, why reality is structured this way. Let's start with the first constraint: the speed of light. In 1905, when Albert Einstein introduced special relativity, the physics community was unsettled. Not because the equations were complicated, but because they revealed an unavoidable conclusion. The speed of light is the ultimate speed limit of the universe, 299,792 kilometers per second. It sounds fast, but for leaving the solar system, it is profoundly insufficient. And worse, this is not a technological issue. It's a law of physics. The moment you try to accelerate an object with mass, something counterintuitive occurs. The faster it moves, the more resistant it becomes to acceleration. Near light speed, even a tiny object demands extreme amounts of energy. To accelerate further, you would need the energy of the entire universe. This is not a challenge. It is a fundamental limit. The second constraint is even more severe: energy conservation. Suppose we somehow construct a spacecraft capable of approaching light speed. How much fuel would it require? The answer is sobering. According to relativistic calculations, accelerating just 1 kilogram of mass to 90% of light speed requires energy comparable to thousands of nuclear explosions. A crewed spacecraft would weigh at least 100 tons. That means you'd need to convert the entire mass of Jupiter into pure energy just to barely begin the journey. Jupiter is a gas giant with 318 times the mass of Earth. And this is just for acceleration. You would need a similar amount of energy to slow down. Without deceleration, arrival becomes destruction. So the energy cost effectively doubles. Some ask, what about nuclear fusion? After all, the sun operates on fusion. In principle, yes. In practice, efficiency becomes the barrier. Even the most optimistic fusion reactions convert only 0.7% of mass into energy. That would require consuming over 1,000 Jupiter-sized masses for a single round trip. Our solar system contains only 8 gas giants. The third constraint is time dilation. The most counterintuitive outcome of relativity. Imagine traveling at near light speed to Proxima Centauri, 4 light years away. For you, the journey lasts 2 years. But when you return to Earth, 10 years have passed. Your children are older. Your parents have aged. Society has changed. Everything familiar is gone. The farther the journey, the more extreme this separation becomes. A trip to the galactic center, 26,000 light-years away, might take you 20 years, but 50,000 years would pass on Earth. Languages disappear. Civilizations vanish. Memories become artifacts. This is not travel. It's time exile. And even if all three constraints were somehow accepted, the solar system itself already presents a vast barrier. Textbooks tell you Neptune's orbit is 4.5 billion kilometers away. But that's only the planets. The true boundary of the solar system is the Oort cloud. A spherical shell of trillions of frozen comets stretching out to 1 light-year 9.46 trillion kilometers. Voyager 1 has been traveling for 47 years at 17 kilometers per second and has covered only 24 billion kilometers. At this speed, crossing the Oort cloud would take roughly 18,000 years. For perspective, human civilization itself is only about 10,000 years old. Some suggest building faster spacecraft. In 1976, NASA launched Helios 2. It remains the fastest human-made object, reaching 70.2 kilometers per second. Fast enough to cross Earth in minutes. Yet even at that speed, crossing the solar system would take over 4,000 years. And those speeds rely on gravity assists. Once you leave the solar system, there are no planets left to steal momentum from. Your speed freezes forever. You become a drifting bullet, never stopping, never slowing, never arriving. What if rockets are abandoned entirely? In 2016, Stephen Hawking and Yuri Milner proposed Breakthrough Starshot, a laser-driven probe reaching 20% of light speed. The idea sounds revolutionary. Until the energy requirements are considered. The system would require a laser array covering 100,000 square meters producing 100 gigawatts of power, comparable to a nation's output. All of that energy to accelerate a 1-gram probe. It cannot slow down. It cannot return. It passes through its destination and disappears into interstellar space. And that probe cannot meaningfully transmit data. A single gram cannot support complex communication systems. In effect, vast energy resources are spent to send a microscopic object on a one-way trajectory. What about crewed missions? Perhaps humans could hibernate for millennia. Wake up at the destination. Medicine offers a difficult answer. The greatest challenge to cryonics is not temperature. It is ice. Freezing forms crystals that rupture cells and destroy genetic structure. Even protective chemicals offer only partial preservation. The brain presents the greatest difficulty. Hundreds of billions of neurons, each connection encoding memory and identity. Disrupt those connections and continuity is lost. Even with perfect preservation, radiation remains unavoidable. Interstellar space is saturated with high-energy particles. Without Earth's atmosphere and magnetic field, DNA damage accumulates. Over long durations, biological systems degrade beyond recovery. What about generation ships? Large, self-contained habitats where multiple generations live and die en route to another world. Popular in science fiction. Unstable in reality. Maintaining genetic diversity alone requires hundreds of individuals. Each requires food, water, and air. A 10,000-year journey demands tens of millions of tons of supplies. The total mass would exceed 100 million tons. Energy requirements return once again. But the deeper issue is social. History shows that closed systems tend toward instability. Purpose erodes. Belief systems fragment. Technological knowledge fades. The mission dissolves. What about wormholes? A theoretical shortcut through space. General relativity allows their mathematics. But stable wormholes require negative energy, a form of matter never observed. For decades, experiments have found none. Even if such matter existed, Maintaining a small wormhole would require energy equivalent to the mass of an entire galaxy. Hundreds of billions of suns. The concept remains mathematical, not physical. Every apparent solution collides with fundamental limits. Every workaround demands conditions beyond reach. And humanity has yet to leave its own solar system. The most profound constraint is not technological. It is cosmic. In 1998, astronomers discovered that the universe's expansion is accelerating. Distant galaxies are moving away at increasing speeds. Driven by dark energy, a phenomenon we do not yet understand, comprising most of the universe's content. Over time, regions of space will become permanently unreachable. Even if other civilizations exist, contact may never occur. Isolation is built into the structure of spacetime. This reframes the Fermi paradox. Civilizations may be common, but they are confined. The Milky Way itself contains around 400 billion stars. Exploring even a fraction would occupy any civilization for immense spans of time. Worlds of every kind exist here. Being limited to this galaxy may not be a punishment. It may be a responsibility. To preserve life. To maintain intelligence. If intelligent observers are rare, we may be the Milky Way's only witnesses. The universe observing itself through a narrow window. So when you look up at the stars, don't see a cage. See an inheritance. We will never leave the Milky Way, not because we failed, but because this is the domain reality permits us to inhabit.